Hello, everybody. Welcome. I hope that you have been enjoying the show so far. I know that we're getting towards the end here these last 3 days, and it's been packed with a ton of great information. I'm excited to share with you today OTA model updates with Edge Impulse and Blues Wireless. And I'll introduce myself and my co-host here right now. So my name is Brandon Satram, and I'm the Vice President of Developer Relations at Blues Wireless. We're an IoT hardware and services company. And I'm joined virtually today by Rob Lauer, who's the head of developer relations. Now, Rob had a family emergency and was unable to actually be here with me on the call, but he was gracious enough to record his session, and I'll be playing that when that gets to that part of the day. So here's what we've got to go through over the course of the next hour. I'm going to spend a few minutes introducing Blues Wireless. And then Rob is going to carry the bulk of the presentation, talking about using Edge Impulse with the note card, our product, and then demoing doing over-the-air model updates of Edge Impulse trained models using the Blues Wireless note card. And then at the very end, I'll come back and I'll do a reintroduction of the Swan, which is a product that we announced 2 days ago during Ray Ozzy's keynote portion of the conference. And then hopefully we'll have a bit of time for Q&A at the end. Feel free to ask questions throughout during the chat. While I'm playing Rob's section, I'll be on YouTube and following along, and I'm happy to answer questions at that point. So very briefly, I want to talk about Blues Wireless, who we are and why we're here today as a part of an Edge ML event. And it really all starts with the complexity of building prototypes, and the complexity, why we exist as a company is because of the challenges of building IoT solutions in today's day and age. And oftentimes the reason why products really tend to struggle in many cases is because building an IoT product requires this crazy mix of skills and capabilities, some of which we as developers are comfortable with, and some that we're not. And so what that ends up leading to is complexity. And Ray mentioned this in his keynote the other day. It's actually a very famous quote from him and his time long before he was in the IoT space. But that idea of complexity, and his quote is that complexity kills. It sucks the life out of developers. It makes products difficult to plan, build, and test. And I'm guessing that even if you haven't heard that quote before, you've lived it, you've felt that experience. And in our space and in the world of IoT, there's definitely a lot of complexity. There are so many problems with wireless IoT connectivity, and it's an area that's rife with landmines and potholes, and what I like to refer to as the strings of wireless IoT. And these are things that developers can't control, or which make our lives difficult. They slow us down, they cut off choice, and they add unnecessary duplication of effort. And there's a lot of these that you can look at, but really the four that I tend to observe the most are difficult to program modems, too narrow or too wide guardrails, pitfalls with device lifecycle management, and then finally security as an afterthought. So let me dig into each of these very, very quickly. If you've ever had to program a connectivity module with AT commands, you've experienced the strings of wireless IoT. Same if you've ever been told you had to adopt your IoT vendor's entire ecosystem down to the MCU, programming language, and IDE just to get a product online. Or if you put off activating a cellular IoT device because you didn't want to start the meter on a monthly data plan, or have to pay for something that you weren't going to use until you were really, really ready to go. Or if you've been forced to embed your keys and certificates in firmware for cloud applications just in order to send that data out. And we know the strings of wireless IoT at Blues Wireless because we've lived many of them in our own products and our own projects. And it's why we created the Note Card and NoteHub.io. And our goal really was to cut those strings of wireless IoT and create a product experience that's simple to start, that is flexible for developers and allowed them to use the tools and the languages that they prefer, but can scale up with your products as you go from one to many devices and ultimately get your data into your cloud applications. And it starts with a note card, which is a low power cellular and GPS module that comes with that has cellular IoT connectivity in over 135 countries. The device comes with 10 years and 500 megs of data. It's baked into the cost of the device. It's written on the tin, as it were. There's no monthly data plans, no activation fees, and you don't have to worry about a ticking clock when you start working on your project. And instead of spending time learning the labyrinth of AT commands unique to every modem, you can use JSON with a note card to simplify, to do everything from configuring the device to adding sensor data to facilitating a connection and more. Really, anything that you can do with a note card, you can do with JSON, which is an easy to learn, easy to understand concept that we can all work with very quickly. And so with the note card, you can actually go from unboxing to sending any data you wish into the cloud in minutes using a secure cellular connection. Every note card already has the keys it needs to connect to the note hub securely baked in the device at the point of manufacture. So there's no key rotation, there's no cloud provisioning process. The note card knows where to go in order to phone home the second that you power it up. And in terms of where that goes, the note card, that's the notehub.io cloud service. And that's where the note card is ready and waiting for your project data once you bring your devices online. It's designed to be a thin middleware layer between your cloud, between the note card and your cloud applications. So we make it very easy to route data out to Azure, GCP, AWS, or other visualization services like Losant, Ubidots, DataCake, you name it, really. Anywhere you want that data to go, we facilitate that connection pretty easily. And so once that data has landed in the cloud and you route it out, you can do the fun part of IoT, right? The reason why many of us get into this space and building visualizations to manage physical assets, to make critical business decisions and all that good stuff. And so what that allows you to do is really focus on building a solution. So you can do things like water quality monitoring or air quality monitoring, or one of my favorites, and this was mentioned in Zach Shelby's keynote on Monday, doing things like EdgeML and actually really bringing the power of your devices to do inferencing on the edge and to send the results up to the cloud, but not stream all of that raw data and all of that potential PII up into your cloud applications. So the note card is available at shop.blues.io and at SparkFun, and it'll be available soon at DigiKey, so you can check it out in any one of those locations. And before I hand it over to Rob to do the rest of the demo, I did want to very briefly show you the product in action. So this is a camera that's actually sitting in my desktop, and this is the note card that's baked in. For some of you that got the kit for the workshop, the note card includes these development accelerators called note carriers, and that's what we have here. It's a Pi hat that's sitting on top of a Raspberry Pi 4, and I also have a Grove BME 680 that's connected to it, and that is really literally just as simple as it is. And my note card is actually connected over serial on my desktop, which allows me to go to dev.blues.io, and I can actually go through the note card quick start from the browser without having to download a CLI tool or anything like that. So this is actually part of the onboarding experience that we have on our developer site. So you can actually go to dev.blues.io, go to the note card quick start, connect your device up, and then very, very quickly start sending JSON commands to it. And so you can enter some of these commands through what we refer to as the web REPL here, and it'll tell you about the device, its version number, all that good stuff. You can set up your connection to the Note Hub. And one of the first things that you'll do when you onboard a new note card is you assign it a product ID. That sort of associates it with a project that you're working on the cloud side. And so I'm using a dummy project name here. But once I've set that, the note card now knows where to go when it actually lands into the Note Hub cloud service. And so if I can add data to it, here I'll just add a note. And the note is just a simple arbitrary JSON body. In this case, it's temperature and humidity data that I'm making up that I would eventually have on my BME, pull out from my BME 680. And then I can actually sync that. You can set up sync rules for the note card, or you can manually sync it to the cloud. And once I've actually issued that request right there, what happens is the note card connects over the cellular network and it will show up in my project. And this project that I have here, my company project, would be where it was going to show up, and it's going to appear online over the course of the next couple of minutes. And then I'll see events sort of starting to stream in as they'll show up. You'll see that as the green flashing light, or there was the green flashing light that went away a second I started showing my camera, was here, but it's actually brokering that connection, and it'll start sort of streaming data to the cloud for me. You can see that a connection has been made recently. And so this is the sort of quick getting started experience, but for many of us, it's not really the place where we're going to be doing most of our development, because a lot of times we're building applications where a host is going to do some work. So for instance, in the demo that Rob's going to show later, we're actually using the Raspberry Pi and the Edge Impulse Python SDK and the Blues Python SDK to actually make a connection to the cloud. And so there's an actual application that'll be written on your single board computer or host microcontroller. So assuming that I can make an SSH connection in here to the device after seeing it disappear on me a few minutes ago, what I could show you is actually the ultimate Python application that I've written that reads from that BME 680. And we'll see if it's actually going to show up on me here or if everything has decided to stop working for live demo modes. The good news is because Rob's demos are not live, I can guarantee you that they're all going to work because they were pre-recorded. So I might have to come back to this one a little bit later because I do want to give Rob an opportunity to actually get into the Edge Impulse part of this. But you'll get to see some more of that Python code as he actually goes through his demo here. And again, the real important point here is that the cloud, the cellular connectivity piece of this is very minor compared to your application. The whole reason you use cellular or Wi-Fi or whatever it might be is to actually get data up to the cloud to do something down the line. But the real fun part is building your host application. And in the case of using Edge Impulse, building the actual the inferencing piece and being able to work with data locally using Edge Impulse and their SDKs. And so I'm going to mute myself, turn my video off, and I'm going to pull Rob. I'm going to swipe over into Rob Lauer here, who's actually going to dig into a little bit more of the OTA model update piece with the note card, with Edge Impulse and beyond.
Hi everyone, welcome, and I'm very sorry I can't be with you live to go through this part of the workshop today, but life happens of course, and actually I think you'll be better off because A, what I demo will actually work, and B, we get to skip over any parts of the demo where we are collectively waiting on builds or other relatively slow steps. So all in all, I'd say it's a win-win. Brandon, of course, will be here to answer any questions you might have, so let's get started. Now imagine, if you will, a scenario where you are remotely deploying a sensor-based solution to monitor multiple machines. Maybe it's in a factory or industrial setting. Why? Well, you know that these machines make some sounds or maybe vibrations in the early stages of a part failure. So you want to watch or listen for these changes to save yourself on replacement and repair costs. So one way to monitor for multiple disparate points of failure is to literally listen for the noises being made and infer or predict early failures using, surprise, machine learning. And if we can catch audio that is similar enough to what we've previously recorded as an early stage failure, we can of course replace the failing part before the whole system goes down. So we deploy this ML solution to listen for these kind of binary states of yes, it's working, or no, it's probably about to fail. So that's a, fairly straightforward scenario, but maybe a bit too simple. We're assuming one state is functional and another state is non-functional, or at least an early stage failure. In reality, we can probably imagine scenarios where there are other sounds coming from the machine. Maybe new sounds, some scary sounds. These lead to other failures in other parts. Now, the problem we have, though, is we've already deployed our monitoring solution to 100 different points in the factory. Right? We don't want to go through and recall all these devices to update the program or the ML model. But what if we could programmatically collect new audio data, push that data to the cloud, create a new ML model, and then redeploy that model? And what if we could do all of this over narrowband cellular, since it's pretty ubiquitous, secure, and reliable? And yes, this would also work over Wi-Fi as well, but A, this is a Blues Wireless workshop, and today we are all about cellular. And B, there are legitimate advantages to cellular in terms of security and coverage. So I'd like to show you how we can do this today. But granted, there are some disclaimers to communicate. First, what I'm about to show you is kind of a POC or an alpha version. It definitely works, but we are effectively at workshop level solution, not production level. And while the note card can use Cat1 cellular, what I'm going to show you today uses two low bandwidth cellular protocols, NB-IoT and LTE-M. These are not great for large file transfers, I'll be totally honest. They are meant to transfer relatively small chunks of string-based sensor data. But you're probably like, Rob, these .eim model files from Edge Impulse are not generally super small, right? They're in the megabytes. Well, I'm going to show you some tricks on how we can actually shrink some important parts of the model files down to just tens of kilobytes before transfer. Next, there is a fair amount of digging into the Edge Impulse APIs and some Python coding to make this happen. Just to warn you, there's some coding involved. There is also a server-side component involved, which I know can be scary for some of us, but everything you see luckily is server-side agnostic. For instance, I happen to write a C# API to do this since I have a .NET background, much to the chagrin of Brandon, but you can do this in Python or Node or Java or whatever you want to write. In fact, I do plan on rewriting this API in Python soon. All right, so how is it all going to work? Well, I'm going to build a new custom audio classification model in Edge Impulse from scratch. I'm going to deploy this model to my device, which today, of course, is a Raspberry Pi 4. Once it's deployed, I'm going to remotely sample some new audio. I'm going to push that audio clip to the cloud. I'm going to transfer it to Edge Impulse and build a new model file. And then I'm going to download and deploy that model back to my device where I can process it for use in a Python program. And the cool thing here is I'm literally going to be using cellular for everything you see within these brackets. Now, even though this is recorded, I promise you I won't be taking any shortcuts at all. This will actually all work. And before we jump in, finally, I don't want you to freak out if you get lost in the code. To me, it truly is more important that you understand this can be done versus literally knowing how to do it today. To that end, there is a GitHub repo here where you can find all the code I'll be showing you today, and I will continue to improve this as time goes on. Because today this code is optimized specifically for audio models, and there's some tweaks we'd have to make to change it for regular file transfers and of other sorts. So with that, I'd like to transfer over to a demo, so I'll share my desktop here in a sec. First, I did want to show the Raspberry Pi that I'll be using for the demo. What you see here is literally what is mounted on my wall over here to the right. This is a Raspberry Pi 4 Model B. It has the note carrier Pi hat with a note card mounted on top of it. That long dangly thing to the left is a Molex antenna, so we can get a good cellular signal even down here in my basement office. And finally, that little USB input there, that's my microphone. I'm using just a cheap off-the-shelf USB mic with the Pi. It's literally plug and play to get it to work. And I think with that, let's switch over to my desktop and get this rolling. All right, I want to start by introducing our four different environments for getting this running end to end. The first is the browser. This is where we're going to be using Edge Impulse Studio, of course, to create our initial model. We're also going to be in Visual Studio Code a little bit. I wanted to show you the actual code that I wrote to make this happen. There's quite a bit of Python and some C# for the server-side API. I also have a VNC connection into my Pi. The reason I did this is so that I could show you the files being assembled literally on the Pi in the file system. Finally, we also have the a Windows VPS set up here, and this is of course, our server-side environment that's going to receive the updated information from our Pi to append to our machine learning model that we're going to create. Okay, and again, the reason I have this open is we can see those files come in and get assembled and then shipped off to Edge Impulse. So let's start in the browser. Now again, this is going to be a complete end-to-end example, so we're going to start from scratch and do this all the way through, and it's going to work perfectly, I have no doubts. We're going to start by creating a new project. This new project, we're going to call this Audio Classification for Machine, right? Something nice and generic. And this is going to be an audio project. And the first thing we want to do is connect our development board. So let's switch over to the Raspberry Pi. And remember, we're pretending that we've not yet deployed the Pi yet, so we can do all these as if we're either have the Pi sitting right here or we're connected to it via Wi-Fi. So in the Pi, the first thing I need to do, assuming I have gone through and set up some dependencies to get the Pi running with Edge Impulse, with the Edge Impulse CLI and such, I'm going to run edge impulse Linux and pass the clean parameter. This is going to allow us to log in fresh and select a new project. I also need to pass the disable camera flag. This is because I don't have a webcam or other camera set up on my Pi, so we want to avoid that error. And with this, I'm going to need to log in. So I'm going to pause recording so I can grab my password. And that seems to have worked. And the project I just created, audio classification for machine. Hey, that's us. And we're going to choose the audio device. Remember, we're going to use that cheap little microphone I added to my Pi. And at this point, oh, we got to give it a name. Let's just call it RPI for short. And we are connected, which is awesome. So we can head back to Edge Impulse Studio. And we can get started. And the first thing we want to do is head to the Devices tab, of course. You can verify that our device is connected. Looks beautiful. Now we need to start acquiring some data. Now remember, we're concerned with two states on our machine, right? We're concerned with it being in normal mode, and we're concerned with some kind of a failure. So let's start sampling some data. We're gonna, we're pretending that we know what a normal mode sounds like. And I'm gonna start sampling some data, supply it, we'll just call it normal. And the sample is gonna be just me making some embarrassing sounds. So we'll have normal either be fairly quiet, so just the ambient noise that you're hearing in my office, which is nothing, or just like a shh sound, okay? So I'm gonna start sampling. All right, that was kind of ridiculous, but hopefully you could hear me by my Pi whispering sweet nothings into the microphone. And I'm going to play it here. You can probably not hear it at all. If you can barely hear a little shushing. I'm going to do this again, maybe a little bit louder shushing. Oh, all right. Let me play this. Just barely hear some shushing sounds. All right, I'm happy with the normal state. Let's have how about a failure state? This, I'm going to pretend our failure state's going to be like a very different sound, like a ba, ba, something like that. So go ahead and listen to me sound like a total idiot again. Ba 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 ba. Oh, this is so fun. And let's play that. Okay, sounds good to me at least. Let's try one more sample. Do this a little bit louder. Ba 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 ba. I hope nobody from work watches this because they will make fun of me. All right, and we've got some failures. So cool. I'm feeling pretty comfortable here. We've got a normal sounding machine, and then what we know is a machine that's about to fail. What I'm probably going to do here is let's split up these samples a little bit because there's only certain segments that I really want to hear. We'll say like that looks like a good one, and say these babas are good, and just this one. I love this UI for splitting up our samples. Let's add another segment here. Now we really, of course, to do a proper model, we need as much data as possible. And what I'm going to put together today is just barely enough to even get this demo to work. But we're going to go with it anyway. And let's grab this failure and quickly split this up. And I will fast forward through this so you don't have to watch me doing a whole lot of this part. Let's call it good. We got some bas in there. And we've got some, let's look at our normal audio, see if we can split this up at all. Looks like we do have some peaks in here that we can, and they did a pretty good job of segmenting it already. Let's do that. And I'm not sure about this one. I'm going to just cut that out. This might be my favorite part, really, because this UI is just so cool. And let's play one of them here. Probably can't hear that, but it's me shushing a little bit. Let's split that up. And the last one is this guy, and we're gonna split you up. Some nice peaks here as well. And in fact, those look really well aligned, so I'm just gonna go with it. Excellent. At this point, we have a decent amount of data, but you can tell right away we have a lot of data for our training data set. We have nothing for our test data set. Thankfully, Edge Impulse makes it much easier than you would otherwise experience to segment out your test and your training data. But we can click on the Perform Train Test Split. So we need to type in Perform Split. And this is going to divide up our data set into training and testing data. And now it's time to create an impulse. So let's head over to the Create Impulse menu option. We're going to add a processing block. And I'm going to really stick just to the recommended options here. We're going to add a learning block. Now we have 2 output features we want to save. Impulse is saved. Next step, let's head over to Audio MFCC to generate some features. So we're going to have 2 specific features. We've got a failure feature and a normal feature. So let's generate those. This is the other beauty of this being a recorded demo. We can buzz through these build steps really quickly. Beautiful. And we can see our feature explorer here out of 22 samples. Boy, look, that segmentation looks beautiful. Completely separate for failure and normal states. Let's head over to our neural network classifier settings. And again, I'm going to leave everything default because frankly, I don't understand half of what's going on here anyway. And we're going to start our training. Excellent, model training complete. Look at that accuracy, 100%. Well, obviously our data set is really limited, so our accuracy should be really good here. Let's finally head over to model testing. You see we have some normal and some failure tests. Let's classify them all just to make sure that our model works correctly. Beautiful. Now we're ready to deploy, frankly. This, as I've said repeatedly, this is a very simple model. From here, what we can do is either we can create a library through the web IDE or the web UI. We can also use the Edge Impulse APIs to create the model, which we will build, or sorry, which we'll do in a little bit later. But in our case, since we are deploying to a Linux board, there's not actually much to do here because we're going to go through and build it using the CLI on the Pi. I'm going to go ahead and analyze the optimizations here just because I'm kind of curious to see if there's a major difference between the quantized versus unoptimized model. Usually for a model of this size and scope, it's pretty negligible difference. As you can see, pretty similar for both of those. So now let's head back over to the Pi. And again, we're going to use our VNC connection here. Let's close out of there. And what we want to do here is run the Edge Impulse Linux runner. And we're going to pass the download parameter to grab that model file. We're going to call it model.eim. And we're going to make sure this goes into the same directory as our Python scripts, which we'll talk about in a sec. In fact, let's talk about it right now while this is building. So these are all of the Python files that are going to live on the Pi when it's deployed. So we'll be able to, as you can see, as they're aptly named, we'll be able to record audio. We're going to be able to post these audio files to the Blues Wireless cloud service called NodeHub, which then will securely relay the data back and forth to and from Edge Impulse. We're also going to configure our note card to listen for these model updates, so these incoming model updates. And finally, we have a run impulse script that simply is going to run this model file so we can test it out. So this is, a very simple end-to-end kind of example. Now you can see that our model file is complete. It's right there, which, yes, means we can run this and see what happens. So using Python 3, let's run the run impulse Python script, and we're going to pass in the model file. And when I run this, we're gonna attempt to see if we can get the error states to pop up here. So let's see. I need to select the audio device we want to use. So this is the microphone that I've hooked up to my Pi. Okay, so in general it's saying it normal, right? Well, some failures are popping up there. Let's get a ba 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 ba, so we can see when I do that ba's. I'm gonna close that down. When I do the ba's, we can see that our failure rates are hitting, which is great. Okay, so in general, we can say that given it, the 2 minutes that I took to build this model, so far we're pretty happy. Now, we need to configure our Pi to accept an updated model file. And this process is far more complicated, unfortunately. There is some ceremony involved, but once it's set up, it works pretty flawlessly. It does involve cloning a GitHub repository to the Pi and running a couple other configuration steps. So let's walk through all of these bit by bit and make sure we're all on the same page here to figure out how to set up a Pi to receive incremental updates to a model file. Our first step is to head over to GitHub to the example standalone inferencing Linux repo supplied by Edge Impulse. And this is the Edge Impulse Linux SDK. So this lets you build, basically mimics what you can do in Edge Impulse Studio, but locally. So you can download this SDK and you can do a heck of a lot of things with it. Installation guide is really well laid out. This is all really straightforward. In fact, there's only a few things you really have to really worry about here on the Pi. I'm going to go through this step by step. So we're going to clone a repo and initialize some submodules here on the Pi. And let's do that right here. And while that's cloning, let's copy and paste my favorite kind of programming here. I know this isn't programming, but my favorite kind of development. And run that. So again, what we're doing here is we're basically shortcutting what we're going to need when we're doing incremental model file updates, because we don't want to update a full EIM file over and over, because that's megabytes and megabytes of data. In fact, we can take a look. Our model.eim is 8.5 megabytes. Too big to download over a narrowband cellular connection. Especially when you start talking about edge devices with way less memory than are even available on the Pi. Go back to our studio here, and we are going to export the same trained impulse as a C++ library. Now you notice when I choose C++ library, we have a new option here to enable the Eon compiler. We actually have to disable that for this scenario. I believe it's because we're using the full distribution of TensorFlow Lite, which there's some incompatibility there, but I could be wrong. And we are going to build. And when I build this, it is going to supply me with a zip file. And that should pop up in just a couple seconds. And there it is, audio classification for machine V2. I'm going to go ahead and transfer this file to my Pi. Looks like we're good here. So, file transfers, we're going to send a file, audio classification machine, that's the one I just did, yep. Excellent. File's been transferred to the desktop. Let's extract this. Again, these are all just manual steps you have to do one time, and we have not yet deployed this remotely, just to level set there, make sure we're all on the same page. I'm going to extract all these to my temp directory, and as that extracts, let's bring my temp directory open here. And it's this one, yes. So at this point, we need, and this is the repo I cloned from GitHub. I'm just going to rename this Edge Impulse to make it a little more simple. I'm going to grab all U, and I'm just going to, you know what, I'm going to copy and paste in here. Done. All right. At this point, we're ready to rebuild our model from scratch just using local resources, so not using the studio at all. To do so, I need to, let's see, let's make sure that we're in the right directory, and we need to get into Edge Impulse. All right, so the command I need is this one, which is basically just going to say build this model, but instead of giving me executable, give me an EIM package. And we're targeting the Linux ARM v7 for the Raspberry Pi, and we're using the full TensorFlow Lite. And fingers crossed, this will just work. And this might take a little bit, but it will generate a model file. It'll in fact be the same model file we got from Edge Impulse Studio. And as that keeps running, we are going to, actually, let's stay in that directory and let this finish. Beautiful. Okay, with my new model file, which is going to be in the build directory, so this was just created, I am going to drop that model file here. So we are going to just overwrite this, and let's make sure it's still running properly. So let's get back to our run impulse pi method and get in the right directory. Again, select the audio device. And it's running there too. So I'm going to go ba ba ba, and we should see some failures showing up. Excellent. So great. It's at this point where we can deploy our Raspberry Pi remotely. So we can pretend in our mystical world that we have taken all of our Raspberry Pis with these files deployed, and we've deployed them throughout the factory. However, we've noticed that some of our machines are making a new sound. It's a new failure sound that wasn't previously recorded. And again, instead of recalling all these back to our devs, we need a way of recording this new audio, pushing that audio to Edge Impulse Studio, and then creating new updated model files that we can download and use locally without, all the other rigmarole. So how are we going to do that? Well, the first thing we need to do is to record some new audio. Luckily, there's a script to do that. And what I'd like to do is spend a few seconds going through some of this code, some of this Python code on the Raspberry Pi client. The first I'll highlight is this record audio script. Now, it's about 50 lines of Python. Pretty straightforward here once you start diving into it. I'm going to kind of gloss over most of it since it just has to do with using the Pi audio library to record a wave file locally. So now that you've seen this code, let's head back to the Pi and actually execute this with our record audio. Now we're recording a new failure, right? My new failure is going to be some claps. I want it to be pretty different from the regular failure and the normal mode, of course. So let's do this. Okay, you can probably hear that. And with that recorded, you can see that we have our original sample.wav file. It's about 256K, converted to an MP3 down to 7.8, back up to 46.5 for a WAV file. So really we went from 256 to 46 with minimal loss introduced there. Okay, it's at this point when we want to send this audio snippet up to Edge Impulse over cellular. So the path this is going to take is going to go from our note card cellular module using narrowband cellular on the Raspberry Pi up to NoteHub, which again is the Blues Wireless Cloud service. NoteHub is going to route this data to the Edge Impulse APIs via the C# web API I created. So before we do this, again, I want to take a look at our code really quickly here. And there's two pieces of code I want to look at. The first is our post to NoteHub Python script. And let's walk through a bit of this. I want to highlight a few things here. You'll notice this chunk size content. What we're going to do is we're going to chunk up this file. We're going to chunk up our WAV file into 8,000 byte segments. The reason we're doing this is that narrowband cellular it's not like 5G, right? You're a bit limited in what you can send. And I want to make sure that our packets get through okay. So with a chunk size of about 8K, that's usually just fine to make sure it gets through over the network without too many problems. We're also going to base64 encode the WAV file on the client, and we need to determine how many chunks we're going to send to NodeHub. That's done with some simple math, basically saying the length of our encoded WAV file divided by the chunk size. We're going to create a GUID to uniquely identify the chunk on the server in case we have multiple files. We don't want them to get mixed up. And as Brandon showed you, we're going to initialize the note card using a NodeHub product UID that I specified in my keys.python file as well, a private key. And let's see, let's skip ahead a little bit here. There's just some error checking that is involved here. We're actually creating an empty list of possible errors, so failed chunks that we may need to retry later. And let's get to the fun part here. For every note chunk we need to send, we're going to execute this send chunk function. This is simply going to execute a web.post request. And again, this is using that friendly JSON API provided by the note card. We're going to hit this post audio file route in NodeHub, which I'll show you in a second. And then we're grabbing up the payload, which is, if you can read this silly looking code, it's really just the segment of the base64 encoded string. And then we're just printing out which chunk we're sending, okay? Kind of a long-winded way of explaining, we're just chunking up a file and we're sending it to NodeHub over cellular. Now on the back end, we've got our C# web API, and that is going to be it's executed with this Edge Impulse audio controller. So again, this API provides a series of methods for accepting this post data that specifically contains a WAV audio file. There's a variety of constants that are pretty self-explanatory, a bunch of keys, local directories. I don't need to dive into all this code. I know it looks a little bit funky in a way, but I think if you read through it line by line, it'll make a lot more sense. But I do want to summarize what's going on here on the server side. So step one here, we're reading this binary data from the post. We're converting it back to base64 because NodeHub is actually going to optimize that base64 data for us and then send it to the C# web API in binary. I want to convert it back to base64 so I can more easily assemble the file locally. And then after that file is written, we need to check the file system to see if we have all the chunks that we expect to get. So this is basically saying, loop through all those files in that directory that contain that GUID and make sure that they match the number that we expect to get. Step 3, if all those chunks are accounted for, let's reassemble that file from scratch. And step 4, very important step. Now we're going to send that WAV file to the Edge Impulse ingestion API. It's a simple web request. We're doing a post, and we are, let's see. The next thing we're doing actually before we execute that post, is we need to extract the WAV data. And I created a helper function to do this. I learned a lot about WAV files during my preparations here. Effectively, what's happening is WAV files have a standard header attached to them that we don't want to send to Edge Impulse. This method simply just extracts the necessary WAV data out of the file and removes the header. And this is a little bit hard to read, but we're putting together a JSON payload here that is formatted according to what the Edge Impulse API is expecting to receive. And that's about it. The rest are my helper functions here that I don't need to dive into. All right, so should we try this out? All right, with our audio file captured on our Pi, the next thing we want to do is ship this data up to NodeHub, which will then securely relay it on to Edge Impulse after assembling the WAV file. So let's do that with the post to NodeHub Python script. And as this runs, we will see the first HTTP post confirmation here, and we'll pop over to the Windows server just to verify that the file is there as expected. Excellent, there's the first one. So in Windows we can see that file show up here. And we should see, I think it's about 6 or 7 or maybe 8 total files that will comprise the entire base64 encoded WAV file, which is all well and good. And I should be clear, like the way that I'm instrumenting this application in particular, it doesn't make a whole lot of sense, and I have all these separate Python files that really are not orchestrated the right way to execute remotely. Ideally, I would have one program that would be running continuously. Obviously, in a deployed scenario, you don't have access to a VNC or necessarily even SSH into it. So there are some some luxuries I'm adding on here to this demo. And actually, this gives me an opportunity to show how simple it is to set up a route in NodeHub to route your data on to any endpoint. So I have two routes. So again, NodeHub is going to take this data from the Pi, and it's going to relay it on, in this case, to a specific endpoint, a custom endpoint that I've created. You can also use NodeHub to route data to Azure, AWS, Google Cloud, a number of IoT optimized platforms like Ubidots and Datacake and such. But this is probably one of the most simple routes you could see, because I'm literally just saying, hey, whatever you send to this route, send on to this URL. And let's see where we're at here. Oh, great. Everything's done. We can check Edge Impulse Studio now. So let's head back over to Studio and look at our data acquisition tab. We should see, and sure enough, there is a new failure data sent over. Let's see what that sounds like, or hear what it sounds like. Maybe you can hear that, some, hand clapping sounds. I'm going to go ahead and split this sample up. Good enough. All right, with this additional data in here, let's go ahead and rebalance our data set again. From that split. And let's go ahead and retrain the model. And once this model is retrained, I now don't have access to the Pi to, directly download a big model file or even build one locally with any downloaded zip file or anything like that. So this is where things deviate from our initial path here. So what I need to do is I need to hit one of the APIs, the server-side APIs I created directly. I can do it either with a browser or with Postman or whatever, because this is where things get pretty interesting to me, actually. In fact, the job did complete, but I do want to start showing off the next set of code here, and that's going to be our model controller. Now, this is the API that's going to provide a series of methods for chunking up a file that it gets from Edge Impulse. So again, we are going to hit some Edge Impulse APIs. We are going to build this model file using all those APIs. We're going to download it to the server itself. Then the server is going to extract only some specific files out of that build package that we need, zip those up, chunk them up, send them back to the note card. A lot of steps going on here, so there's quite a bit of code, but I think it all is going to make a lot of sense. Again, we're sticking to the same chunk size of 8,000 bytes. Step one here is to build that model in Edge Impulse. So we're hitting specific Edge Impulse APIs to build the model. And step two is to check the status of the build job. We want to make sure it's successfully completed. Once it's done, we're going to download the model file to the server. So it's going to be just a zip package, the same zip that we got before when we did this locally. We're going to clean up some files to make sure we don't have any conflicts. We're going to write out that zip file we downloaded from Edge Impulse. We're going to unzip it. And this is where it gets a little more interesting, because we are deleting the Edge Impulse SDK and the CMakeless text file because A, they're already on the Pi, but more importantly, B, that Edge Impulse SDK directory is pretty large, and we don't have to, and we certainly don't want to ship this over cellular time and time again whenever we're updating a model file. Once we've done that, we can re-zip up this trimmed up directory, convert it to a base64 string, and save it to a text file. Then again, same thing we're doing in Python. We're going to determine the number of file chunks we need to split it into, and we're going to chunk that file up. And I'll show you all of these files on the server as this happens. Once that's done on the server, so we have our base64 encoded model file all chunked up into these beautiful little segments, we're then going to send an inbound event. So we're sending an event from the server back to NoteHub down to the note card to say, hey, there's a new file you need to download. And we're going to do that with a specific API call to NoteHub. And we are going to pass in this JSON request, which is just saying, hey, add a new note, add a new event, if you will. The note file name is just called model-update.qi. This is what our Python program is going to know to look for. The name of the file that we're sending from the server is this model file optimized text file. Again, base 64 encoded string. And here's the total number of chunks. All right. Now, once that is done, and we'll come back to this. In fact, maybe we should just stop right there for a moment and get that far. So we're going to go back to our browser again. We're going to hit, using this product ID, we're going to hit this API. And as we hit this, let's head to our server and see what happens here, because this is when we're doing the build on Edge Impulse, and we're downloading a zip file, we're extracting that zip file, we're deleting what we don't want, and we're re-zipping it up. A lot of steps involved here, but it's going to take us from, about a 9 meg file all the way down to like tens of kilobytes. Excellent. So let me refresh this so we get some better organization. Oh, I see, it's sorting by name. So what we see here is this is the initial model file that we downloaded. Actually, all right, so 4.7 megs, still pretty big. We extracted it here, deleted some directories we don't need, so we're just left with these two, the model params and tflight model directories. We are going to then re-zip this up. It gets zipped up into this model file optimized down to 12K. We're going to convert this into a base 64 encoded string and save it to a text file, which is our model file optimized text. This is the file we want to send out, and we're going to send it in 2 chunks. 1 chunk, 2 chunks. All right. So now that we have this on the server, then our Pi is going to go ahead and request this by saying, listen for a model update. And you can see it's requesting the first chunk here, requesting the second chunk. And I'm going to show you this code after this is done because it runs pretty quickly. There's actually a lot that goes on. And you can see it's executing that build, which we're initiating remotely. All right, it's all done. We can kill that off. So what we should see here is this model EIM file that was just last updated. Our times match, so this was just updated. So actually this is kind of our grand finale here, but first I want to show the code behind what we just did. So our listen for model update. This again is going to put our note card, our Raspberry Pi, in a state where it's constantly looking for model file updates. And just to double check and show what's going on here, there are a variety of events that are stored in NoteHub that are coming from our Pi. Here is the event that we just initiated. So this is the model update QI file, basically saying here's the file name and there's a couple chunks to be sent. And we're initiating our connection to the note card. I'm going to skip to the bottom here so we can walk through this kind of sequentially. We have a get updated file info method that's basically going to say, hey, is there an updated file from NoteHub to look for? And if there is, what's the file name? How many chunks? Then loop through and say, hey, for each chunk, go ahead and grab it. There's some error checking in here that I'm kind of glossing over here. But this is a key method here. So we need to use the get file from remote method here, which is this method. It's going to go through, basically going to loop through all the chunks that it's expecting and executing the web get chunk method, which is saying what file and which chunk, which is right here. And this is where you get to that specific request. So I'm sending a get request to NoteHub to say, hey, apparently there's a new file I need to get, and you need to send it to me because this is the route that we're going to use from NoteHub. So I'm going to call this route, and this route is going to then call my C# API and say, for this file name and this chunk, send me the file. And it takes that payload and just returns it as a string. Once I have all the files, once I have all the chunks rather, we then go through and we put them all together. We decode that base 64 decoded file. We write it out as a zip file, because that's the original format, right? And this is where we get into this kind of complex directory management. But basically, we are extracting that zip archive. We're deleting the existing model params and TF-Lite model directories from our initial Edge Impulse SDK distribution, or our model distribution. We're then copying these new directories into the old one. And then this is what I love about Python. I can just send this terminal command, and it's going to build the new model file for us. Remember, this is the exact code that I ran in the terminal. At the very end, I have this new model file. I'm just going to copy that up from the build directory up into our application directory. That's it. Now we're ready to roll. So let's go back here and see how this worked. So remember, I added like a clapping sound. And we're going to run the default one. So again, not hitting many failures here. Oh, there's some that are showing up. When I have specific failures, again, it's a little sketchy because my model is pretty weak. But when you can see when I was hitting specifically like those claps, that's when I was getting the failure notification for sure. So I'm going to call this a success, because I think we saw from beginning to end how this was all put together. In a real world scenario, I'd say I probably took you about 80% of the way. There are a lot of, little nuances to deal with. The biggest one probably being the number of data elements you add to your Edge Impulse model. I think we've all seen the more and the better data we have, the more accurate our model is going to be. So with that, I thank you very much for attending. I hope you've learned something or been inspired by something here. Again, you can consult that GitHub repo that I added to the slides as a reference, and we will continually update that and improve that as time goes on, since right now, like I said, it is optimized for WAV audio files only, but you can certainly use this for raw file transmission as well of any sort. And yeah, I hope you enjoyed it. All right, thank you.
That was a lot. I know that there was a ton in there that Rob has covered over the course of the last 45 minutes or so. Hopefully, if you were following along, you did see that he has the code that he'll be that we've posted online, and we'll share the links to that later. And in the last 2 or 3 minutes that we have left, I did want to very briefly talk about Swan. I'm sure you saw there's some questions, chat back and forth about Swan. If you missed the announcement from a couple of days ago, we, Blues Wireless, did release a new microcontroller called Swan last week. It is actually a dev board, not a waterfowl. And we really love this board because we sort of see it as sort of the edge inferencing microcontroller. It's an ARM cortex-m4 STM32 L4R5. So the L4 series is the low power family of boards. It clocks in at 120 megahertz with 2 megs of RAM, 640K of flash. I heard Lady Ada herself say this on the Ask an Engineer Adafruit live stream the other night. 2 megs of RAM, that's a ton for a microcontroller. So this is a pretty beefy board. It is Feather compatible, so we actually ship it as a board that you can use with any Feather wing that you can put male Feather headers on. But it also has a set of castellated edges that allow you to solder it right down onto a baseboard. And we have a carrier for this that comes with the Swan itself that you can buy. And that allows you to leverage 55 pins on the STM32 processor. You can check it out at bit.ly/swan-mcu. That's where you can learn more about it. We have quick starts for it, and it supports C, C++, Arduino, and CircuitPython, all of those out of the box. We're pretty excited about it. And most of all, and best of all, the Edge Impulse team, and we have been working with them on this for a while now. If you go to bit.ly/swan-guide, there's a full guide and instructions on using the Swan with the Edge Impulse SDK. So we wrote a complete guide that's linked to from the Edge Impulse docs on our docs at dev.blues.io that actually show you how you can use Swan and the serial ingestion engine, or the serial SDK that Edge Impulse has created to capture data, send it up to Edge Impulse to train a model, and then pull it back down onto the device. And all of that is covered in that guide. So that is all we had today. I think we ended up ending sort of right on time. So thank you so much. Again, thank you for joining us in this. If you have any questions for myself or for Rob, you can reach us at brandon@blues.io or rob@blues.io. Visit us on dev.blues.io. And I'm going to stick around in the chat and answer any questions that have popped up since I came back on. But thank you all very much and enjoy your weekend.